Great, thank you for all coming. Can everyone hear me? Great. So I want to talk to you today about a problem that is actually sort of obvious and simple, but it took us a lot of time to get it right. And that problem is what you do when you have a machine learning model that's actually changing behavior in the wild. And I'll sort of be clear about what that means as I go on this talk. So I wanted to start by saying a little bit about Stripe. Stripe is a platform for doing business on the internet, and that means a set of APIs and tools for taking payments and for doing other things like analytics and fraud detection. This is an example of just how much code it takes to charge a credit card with Stripe. So you're a business, maybe you're selling classes for Python or you're selling tables, you want to charge credit cards. It used to be the case that you'd have to go to your local bank, get a merchant account, do a crazy integration, parse some really terrible XML or whatnot, and now you can just charge your cards with a few lines of Python or a few lines of Ruby or Go if you use Stripe. So the idea here is that it's just very quick to onboard your company and to start taking payments and doing other things related to running your business. So the machine learning team at Stripe right now has 10 people, and there's no distinction between engineers and data scientists. We hire people who are primarily statisticians by their backgrounds. We hire people who are primarily engineers, but everyone is expected to do both jobs. So no matter what sort of your background is, people converge to this middle ground of both building models and productionizing the code and being responsible for things operationally. So our focus has been on fraud detection for the past couple of years, and that means two things. One, it means that we have to evaluate every business that signs up for Stripe to determine if that business is trying to use Stripe just to charge stolen credit cards. And the other thing that we do is every time a charge comes in, we have to seamlessly score it as part of the charging flow to determine if it's fraud or not. And we do this to defend our good merchants from fraudsters. Just to give you a sense of what happens if you use Stripe or how the charging flow works. So let's say you're PyData and you are selling registrations for this conference online. So what normally happens is that you have a website, say the PyData website, where you take in customer information, the name of the person, the credit card number, the expiration date of the card, and so forth. But one thing you want to avoid as PyData is taking possession of credit card numbers themselves. Because if you have credit card numbers, there are a number of extra security burdens you have to deal with. You have to make sure that you satisfy what are called PCI compliance regulations, which mandate how secure you are if you're ever in possession of credit card numbers. So what happens is, let's say you are a customer and you submit your registration to PyData. Instead of submitting that information to PyData servers directly, the first step is the form gets posted to the Stripe API. So this is step one here. Then Stripe takes that card number and returns a random token. And then the customer's web browser submits that token in step 3 to the PyData web server. And then PyData can say, I now want to charge this token for $100. So the idea here is that this token is a string that can only be charged once. And the credit card information or anything that's sensitive never actually gets exposed to the merchant's web server. So this is how the charging process works. And from a machine learning standpoint, there are two interesting parts here. One is this first exchange, the tokenization, because here the client browser is interacting directly with Stripe. So we get information like the IP address of the user agent, and so forth. So there's a lot of rich information about potential fraud from this first step. Then in this last step, step 4, where we actually charge the token, we're getting some other information like the amount of the charge or the shipping address if one is relevant. So in building a machine learning model to catch fraud, we have to aggregate information from both the tokenization step and the charge step. So that's roughly the basics of how we make charges. Any questions about this diagram or anything that I just mentioned? All right, so let's say you're taking charges. A charge has been made for a counterfeit registration. What are the things that can happen here? The best case scenario is that nothing happens. So the charge is made and everything is fine. Another possibility, obviously, is that the customer requests a refund. This sort of happens pretty normally in the course of business. The case that we want to defend against is when the charge is charged back or disputed. So if you ever look at your online credit card statement portal, this is mine from American Express, if you ever expand a charge, there's this link that says dispute or inquire about this charge. So if you're looking at your statement, sometimes you may notice something that is not a charge that you've made. You can charge it back or dispute it and tell American Express or Chase or whoever that you think this is fraudulent. So what we're trying to do is we're trying to detect events where the authorized cardholder did not make the charge, because those end up being charged back or disputed, and that means that the merchant loses the funds for that charge and also gets penalized a $15 fee. So the TLDR here is that chargebacks are bad, and we want to detect unauthorized uses of cards before they happen. One thing that's hard about this is that credit card statements close once a month, so it often takes several months before someone notices and reports fraud. So it's the case that a charge made today may only get reported as fraudulent to Stripe in 2 or 3 months. So there's a very, very distinct delay here. But just to sort of set the framework of what we're going to talk about, we're trying to detect and stop fraudulent transactions. So let's say it's the end of 2013, and this is actually approximately true for the Stripe timeline. It's the end of 2013, and there has been no fraud detection to date. So for all of Stripe's history up until the end of the year, we were just letting fraud through, and that isn't quite true, but let's say it was. We're letting fraud through, charges were getting charged back, and we decided we have to build a machine learning model to detect and stop fraud. So we want to build a binary classifier that says for every charge that comes in, this is the probability that it will eventually get charged back or disputed. And there are a bunch of features that can go in here, like the client IP country, the card in which the country was issued, the recent history of the IP address, and the card number. But the important part here is that we're building a binary classifier to detect fraud. So let's say we train it on data from January 1st to September 30th. So we have 9 months of data to train it on, and then we validate it on data from October. And we're skipping November and December data because of this 2-month lag in getting the labels. Like, we want to wait at least 60 days before we know that a charge will get charged back or not. So we build a model, and we look at the precision and recall curves and the ROC curve, and they all look fairly good. Is everyone familiar with the terms precision and recall? Right, so precision is of the charges that the model thinks are fraud, what fraction are actually fraud? And recall is of all the charges that are fraud in the world, what fraction did we catch? So if you look at this top graph, this is saying that at some threshold, I'm looking at the top right here, there's a precision of approximately 0.8 and a recall of approximately 0.7. So we're catching 70% of all fraud, and 80% of the things that we flag are actually fraudulent. Is there a question back there?
Sure. So are you doing account-based detection or transaction-based?
What I'm talking about right now is all transactions. Right, so every time a charge comes in, every single one we score independently and block or not depending on its score. All right, so we have the ROC curve, we have the precision recall curve. They look fine, and we decide to action this model by saying we're going to block a charge if the score is above 50. And we've made some precision or recall trade-off that we like. So we put this into production beginning of 2014, and we start blocking charges based on the model scores. So the first question that arises is, we trained this model on data ending in September. We validated it on data from October, and now it's January. So how well is the model doing? Or a more precise question is, what are the production precision and recall? So what fraction of charges being blocked in production are actually fraudulent? And what fraction of all fraud are we catching with this model? So that's one question. And let's say in January or February, a particular business complains to us and says, we're getting lots of reports that you are blocking charges that actually aren't fraud. So the false positive rate is higher than we'd like. So maybe we'll consider something like raising the policy here to block only the scores above 70, so we're a little less stringent. So both of these questions have something in common, which is that they're hard to answer. Does anyone have an idea of why these are difficult to answer?
Can't go back in time and do something different. Already made decisions.
Right, so we're blocking charges, and when we block them, we can't observe the outcome. Right, we care about charges that are going to get disputed. But if we block these 1,000 charges, we don't know what will happen to them. The charges never happen, so we can't observe the labels. Right, so for policy evaluation and for model evaluation, because we're not able to observe the outcomes that we're trying to prevent, we actually can't very easily answer these questions. So we'll get back to this shortly. So here's another issue. So let's say it's the end of the year. It's December 31st, 2014. The model has been running in production for a full year, and now we decide, all right, it's been a year. It's time to retrain the model. So we do exactly the same thing we did a year earlier. We train on data from January 1st to September 30th, and then we validate on data from October 1st to October 31st. So again, remember here that we're building a model on charges, and the target for the binary classifier is, was the charge disputed or not? Was the charge reported as fraud by the cardholder? So we train on more recent data. We sort of have the exact same parameters, and let's even say that the model features are about the same. So we look at the validation data, again from October of the more recent year, and it looks substantially worse than it did a year earlier. Right? For the 2013 data, we had an ROC or an AUC of something like 0.93. Now it's dropped to 0.70. So not nearly as good as we thought it was going to be, or that it was previously. So let's say, all right, we'll just give this a shot anyway, and we test it in production by seeing what it would block, and the results are just terrible. We say, okay, this new model would block these 1,000 charges. We take a human to inspect them manually. They don't look like fraud, and maybe we get a lot of reports from businesses that are saying you're blocking way too many good charges now. So the methodology was the same. All the parameters were the same. Nothing changed about how we built the model, except that we moved this window for training and validation a year in the future. So why are things so much worse now? That's right. So I guess somewhat obviously, for 2014, we were already blocking a lot of fraud. Right? So all of this fraud that we would have seen, we never got to observe. So now we're feeding into this model all of these transactions, and all the ones that are fraud are the ones that were not caught by the model already running. So what's happening here is we're not training a model on all of fraud. We're training one on the residual, or on the fraud that wasn't caught by the previous model. And what's sort of interesting about that is we're essentially training a model on the hardest fraud, or the stuff that we didn't catch before. So it's not surprising that the performance is pretty bad compared to the original model. All right, so what can we do about this? We could, in theory, run both models in parallel. We could say, let's run the old model from 2013 and the new model from 2014 at the same time. So that way we're catching the base fraud, and then we're also catching the new harder residual fraud with the newer model. But we still have the problem with that of how do we evaluate this combination? Like, we can't estimate precision and recall because we don't have the labels in general. So even if we try something like running this ensemble in parallel, we really have no good way to say how well this combination of models is doing. So all of these problems, or all of these questions, have the same underlying problem. We're making an intervention. We can't evaluate the labels. So we can't do model evaluation, we can't do policy evaluation, and we can't retrain the model in an unbiased way. Just saying what I said now. So what we want in all of these cases is an estimate of the distribution that would exist if there were no blocking or no intervention in production. Right, to be able to say, here's the precision, here's the recall, to be able to train a new model. We want an example, or we want an estimate of the charge stream that would exist if we weren't blocking. Right? We want to say, here are the charges and here are the labels that would be in the world if there were no model that were changing behavior. So how can we do that?
Use a sample flight
duplicate action just lately.
Right, so the first iteration is just to say, why don't we just sample from the charges that we would ordinarily block? So let's say if our policy is block if the score is above 50, we'll normally do that, but let's say for 5% of charges, we'll just allow them to go through. Right, so we're not going to block everything, we'll block mostly everything, but we'll have this holdout set in production to see what happens to them. So it's pretty easy to compute the precision of your model if you do this. For the 5% of charges that you let through, you just ask what fraction of them end up getting disputed, and that's your precision. So what about recall? So we're going to let through 5% of the charges that we think are fraud. How do we estimate the total number of charges or the total fraction of fraud that we're catching? So let's do that calculation. So let's say that there are 1 million charges, and 900,000 of them have a score below 50. So the model says they're fine, they're not fraud, let's not do anything about them. And 100,000 of them have a score above 50, which the model would ordinarily block. So first, for those with a score below 50, we got to observe the outcomes because we don't block them. So let's say 890,000 of them end up being fine, and 10,000 of them are blocked, or sorry, are disputed as fraudulent. So we got to observe the outcomes for all the charges that are below the score threshold. Now for the ones above the threshold, we're only letting 5% of them through. So for the other 95%, we block them, and we can never observe the outcome. So that's this bottom row here. So for the 5,000 that we let through, let's say that 1,000 of them are not fraud, i.e. they were never disputed or charged back, and 4,000 were. So in total, we've seen 14,000 chargeback events. But that actually isn't the total amount of fraud. The total amount of fraud that we caught is 4,000 times 20. Because you can imagine we're only letting through 1 out of every 20 cases that we would have blocked. So for the 4,000 examples of fraud that we observed, there are 19 other examples that we did not observe because they were blocked. So we scale the amount of caught fraud by this factor 1 over 0.05. So there are 80,000 cases of, quote, caught fraud, and 10,000 of uncaught fraud. So the recall is 80,000 over 90,000, or 89%. So any questions about this computation? All right, so we're letting through 5% of charges, and we can compute precision and recall directly by doing this estimate. So what about training? So just as before, we're only going to train on samples where we have the label, where we've observed the outcome. But now what we'll do is, for charges that would have been blocked, but we let through this 5% holdout, we're going to weight them by a factor of 20. Again, for the same reason, that for every charge that we would have blocked, but that we let through and ended up getting disputed, there are actually, in quotation marks, 20 such samples in the unconditional distribution if we hadn't been blocking at all. So we're training random forest here, for example, and we pass in sample weights, and the weights are 1 for the samples that, or the charges that we wouldn't have blocked, and we weight the ones that we would have blocked but let through by 20, and the ones that we did block and never observe the outcomes for, we just forget about completely. So we're only training if we can observe the outcome, and we weight the outcomes or the samples by 1 over the probability that we allowed it to pass through a production. Any questions about this?
Yeah.
Yeah, back there.
Of the 95,000 that you got, why don't you just take the ones that were reported as not fraud by a customer? Then you can classify ones that are fraud and ones that are not.
So for the, you're saying for this last row here?
Yeah, instead of letting 5,000 in, why don't you just take the 100,000 and the ones that are not fraud, the ones that are misclassified, will be reported by a customer.
So you're saying we'll just block everything that we think is fraud, and if they are misclassified, we'll sort of let people tell us that.
Yeah, I think the customers will get back to you.
So it is actually the case now that there are methods in the Stripe API and the dashboard that allow businesses to tell us if they think something is fraud or not. It just turns out to be the case that these tools aren't used as much as you would think, right? And there's definitely a bias for reporting false positives over false negatives, because merchants or businesses can't always tell by human inspection if something is fraud or not. Right, so it's true that if something is a false positive, maybe it will get reported by the business. But if something is a false negative, that will often go from undetected. So like asking for human reports, that does add value, but it's not as clean a signal as we can get by seeing what does happen eventually. Does that make sense?
Yeah.
Okay, so we have this data set now where some samples are weighted, and we use the weights both in our model evaluation, in our model training, and you can pass the weights directly in to a lot of scikit-learn classifiers, as we do here for the random forest regressor. And you want to do the same thing in validation. So when you're computing your ROC curve, you're doing whatever you do for cross-validation, you want to include the weights there as well. Right, because we have to pretend as if every charge that would have been blocked that was let through, there were actually 20 such charges, and we want to include that estimate in the training and the validation. So where we are right now is we are saying if the score is below 50, then we allow the charge to go through no matter what. And if the score is above 50, we'll block it with probability 0.95, and we'll let it go through the probability 0.05. So we have the step function here, which tells you what we're doing, right? The probability that we allow the charge is constantly 1 for scores below 50, and it's constantly 0.05 for scores above 50. So can anyone think of why this setup might not be ideal? That's right. So we have to remember that there's a business cost to doing this. If a transaction has a score of 75 and we let it through, then it could get charged back, and then the customer has to eat the cost of this dispute and the fee and all of that. So we're doing this evaluation, and we're doing it because we want the model to get better, but there's a real cost to doing it. Right, we're actually allowing more fraud to happen than we would if we just said block everything if the score is above 50. So let's imagine now that as a business policy, we say something like, we're willing to only let through an additional, let's say, 1,000 disputes or chargebacks per month. So we actually now have a budget for doing this evaluation. We're allowed to let some things through so we can observe the outcomes and evaluate our models, but we're only willing to incur 1,000 extra chargebacks per month. So would our policy about what we let through change? Right now, we're letting through 5% of anything above a score of 50. If we want to maximally or optimally use our budget for model evaluation, how would this policy change?
We can have a smoother curve, I guess.
Yeah, we can have a smoother curve. So one thing about this is that if a charge has a score of 100, it's much more likely to be fraud than if a charge has a score of 50, right? If our classifier is any good. So the area in which there's the most uncertainty is right around the threshold of 50. Right there, it's much more likely that we're making mistakes for charges that have a score of 51 than it is that we're making mistakes for charges that have a score of 100. Right? If it's 50, it's 50-50 that the charge is fraudulent. If the score is 100, it's almost certainly fraud. So if we're only going to let through a certain number of charges per month as part of this model evaluation budget, we want to selectively let through charges in the area where we're most uncertain, and that means right around the threshold of 50. So instead of a step function, we can have something that's smoother. And this is definitely way too smooth, but it gives you an example of the idea. So what we want here is a function that maps the classifier score to what you might call a propensity score. And the propensity score is the probability that we allow the charge to go through. And what we want is that the propensity score is pretty high if the classifier score is say in the 50s, but there's a lot of uncertainty, and we want the propensity score to be low for charges that we're pretty confident are fraud. So we're getting more information in the regime where there's the most uncertainty. Any questions about the setup? Yeah.
I guess in this graph you are learning more in the sense of the observations that are close to 50, but also you are taking more cost on the customer side as well, right? When you change the curve, maybe more smoother.
So the question is, we're learning more around a score of 50, but there's more cost to the customer? Right, so one thing that this graph does not do, but which I should have said, is that you want to imagine that the area under these two curves is the same. So we're not actually we're not letting through more, we're just moving the weight from the top end to the bottom end. Or what I'm saying, what I mean is that there used to be a uniform distribution between 50 and 100 for what we let through. And what we actually want is to let through far more at 50 and to let through far less at 100. So the total number of charges we're letting through is the same. We're just we're letting more through for the lower scoring charges. And that's actually fine, because more of the charges that have a score of, say, 55 are much more likely to be false positives than the charges that have a score of 100. Right, so we're letting through charges that are more likely to be not fraud as part of this change in policy. Yeah.
So two questions. What's the actual distribution of the classifier scores, and why not also experiment with like scores that are slightly lower than 50? Why have a hard cutoff?
So two questions. One question is, what is the distribution of scores like, I guess, for these models in production? And the score distribution is very bimodal. So over 99% of scores are, say, between 0 and 1 on a 100-point scale. You'll have what looks like a very steep exponential past that, and then another blip at around 100. Okay, so it's something like that. And then the second question was, why don't we experiment for lower thresholds? Is that the question? So,
Just smoothness all around.
So that's a great question. So why is it only smooth on one side but not on the other side? Right? Why is there's this phase transition where it's constantly 1 until it hits 50, and then we start dropping off there?
Because you automatically get feedback if you let the charge through.
That's right. Because for scores below 50, we already get to observe the outcome. And let's say we've decided, based on the precision and recall trade-off, that 50 is the right number. So if something has a score of 40, we can observe the outcome anyway. And we gain no information by reversing something that we would let through and blocking it. That's just a way to introduce an additional false positive. Does that answer your question? Okay. All right, so we have this smooth sigmoid now. Sorry, question in the back.
Yes. Do you have to say anything about the actual cost? So precision recall doesn't take into account the size of one of these charges. You can imagine everything above $10,000, just flag it immediately in manual review, and then there's some other bucket for model effectively. Because there's the actual loss function is dollars.
That's right. That's a good point. So everything that I'm doing right now, I'm talking about charge counts, but it's all generalizable, and in reality, we do this both for count and for volume. Right, so you actually, depending on the nature of the business, sometimes counts matter more, sometimes volume matters more. And we have models for both things by dollar volume and just by count. Yeah, right here.
So, and I'm not sure if this is actually the case, I'm curious. When you're doing that curve, so you have kind of a very severe representation of your above 50 scores, does that skew your classifier at the same time as well? Like how, if it does, then how do you account for that?
Oh, what do you mean by skew the classifier?
You basically have like a preponderance of like the scores that are 51 versus scores that are 100. Your examples that are 100.
So yes, we're letting through way more things that have a score of 51 and have a score of 100. So if we rebuild a model just based on what gets let through, then charges with a score of 51 do get sort of too much weight in the model. So we'll address this in the next few slides. Okay. So just to sort of give you in code the idea of what's happening here, the charge comes in, we have the classifier score. We pass that classifier score into this propensity function, which is the sort of half sigmoid that you see here. And then we say, all right, well, the original action is just determined by comparing the score to 50. And then the action we will take, we just say, pick a random number, and if that number is less than the propensity score, then we allow the transaction to go through. If not, then we block the transaction. And every time we do this, we want to record a few things. We want to record the charge ID, we want to record the classifier score, we want to record the propensity score, and then both the original action, i.e. the action we have taken just based on the classifier, and the selected action, the action that we would take based on this propensity function. So let's say, here's an example of a sequence of charges. So what happens here? For charge 1, it has a score of 10. That maps to this flat region in this propensity function here. So the probability that we allow it is 1.0. The original action is to allow it. The chosen action is to allow it. We get to observe the outcome. The charge is OK. Let's say for the second charge, it has a score of 45. Again, that's below 50. So the probability that we allow it is 1. We do allow it. We choose to allow it. And we get to observe the outcome, and it's fraud. So charge 3 has a score of 55. That corresponds to the probability of 0.3 that we allow it. So now we're in this smooth sloping part of the propensity function. We end up blocking, the original action, because the score is above 50, is to block it. And we do end up blocking it based on this comparison of the propensity score to the random number, and there's no outcome to be observed. For charge 4, has a score of 65. The probability that we allow it is 0.2. We would choose to block it because the score is above 50. But based on this random comparison, we allow it, and we can observe the outcome, which is fraud. And just a couple more examples. Score of 100. Probability that we allowed is very small. We would block it in the ordinary world. Random action is also to block it, so we can observe the outcome. And finally, let's say that there's a charge of a score of 60. Probability that we allowed is 0.25. We would ordinarily block it, but we randomly choose to allow it in this case, and we observe the outcome, and it's OK. So as we're doing this production, we have a log line for every action, and each log line looks like this, like a row in this table. And then we can take this table and do some analysis with it. So for example, well, first, we only want to consider charges that were allowed, right? Because if we block a charge, then we can't observe the outcome. And then what do we do for the charges that we do allow? Sort of per your question earlier, we don't just include them with uniform weight in the evaluation and training data set. What we want to do is we want to weight each charge by 1 over the probability that we allow it. So you can imagine that if we allow a charge the probability 0.1, and we see that it becomes a dispute, then there were 10 charges in total, 9 of which we didn't allow, that were not observed, but would have likely been disputed. So for every charge, or previously we were weighting by just 20, because we were letting every charge through the same probability. And now every charge has a different probability of being let through, and we'll want to weight by 1 over that probability in evaluation and training. So some examples. So I floated out all of the charges that were not, for which we didn't observe an outcome. So we only got to observe an outcome for 4 charges, 1, 2, 4, and 6. So I've also added a column here for the weight, where the weight is 1 over probability that we allow, right? So if we allow the probability 0.2, the weight is 5. If we allow the probability 0.25, the weight is 4. So we have this table now, and let's say I ask, what are the precision and recall of the policy when we block charges if the score is above 50? So we got to observe these 4 charges, and the question is, what are the model of precision and recall based on the production data if we're blocking charges with a score above 50? So let's do precision first. There are 2 charges in count that have a score above 50, 4 and 6. But we can't just count them. We have to include their weights, because charge 4 is actually one of 5 similar charges, We just didn't get to observe the other 4. And similarly for charge 6. So we actually want to think of this as there are 9 charges with a score above 50. And of those 9, 5 were fraudulent. Right, so the precision is 5/9. And then for recall, so there are 2 charges here in count that were fraudulent, numbers 2 and number 4. But when you weight them, there are 6 by weight, and 5 out of 6 of them have a score above 50. So the recall is 5 out of 6, or 0.83. So questions about this calculation? Let's do one other one. So the exact same table. Let's say now we wanted to figure out, what if we change our policy to block only if the score is above 40? What's the precision of that? Well, now there are 3 charges in count with a score above 40. But there are 10 in weight, right? Numbers 2, 4, and 6 have a weight of 1, 5, and 4. And of those, 6 out of 10 in weight were actually fraud. So the precision is 0.6. And for recall, there were 6 charges in weight that were fraud, and all of them had a score above 40. So the recall is 1. So the idea here is that for every charge you let through, you pretend that it has 1 over probability that you allow the charge, samples in the underlying data set, and you do all your evaluation and model training based on those weights. I'm just going to skip those other calculations, the exact same thing. So this function that we have, like this step function that turns into this sigmoid, it controls what you might call the exploration, exploitation, payoff. This is actually a bandit problem, right? So the more you let through, the more data you get to train future models, and the more data you get to evaluate the current model, but the less you are exploiting the benefit of your current model, like the less you are catching and blocking fraud. Similarly, the steeper that sigmoid is, the more fraud you're catching, but you're giving yourself less opportunity to explore new possible models and do model evaluation. So all of these things that we're computing, the precision, the recall, these are all estimates because we're estimating the distribution that exists without the model blocking. And the more that we let through, the less the variance we introduce for these estimates. And one thing that you definitely want to do is you actually want to bootstrap these computations. So what we would do here is if we had enough data, we would continually resample from this table, uniformly at random from the rows, do this computation again, and then we get error bars on the precision and the recall. And this whole methodology comes from a paper on search result ranking written by a few people at Microsoft and Facebook. So I recommend reading this paper listed here for more detailed information. I just want to finish up with a couple of technical issues. So there's actually a pretty clear security is the wrong word, but there's a pretty bad weakness in what I've described here in terms of defending businesses against fraud. So any idea what that might be?
Intentionally allow some fraudulent transactions.
Well, that's definitely true, but we know that. We know we're doing that. So if you go up, sorry for scrolling back, all the way here, at 100, that red line isn't at 0. Let's say it's at 0.001. So what that means is that if you're a fraudster and you catch on to this, you know that if you just try the same card 100 times, there's a good chance it'll go through. Right, so you can just essentially take whatever you were doing and multiply it by 100, and now you're almost guaranteed that something will eventually get through and you can observe the outcome if you're testing the card or actually go buy the thing. So what you actually want to do is you want to do something like you don't make a random coin flip for every charge. You compare your propensity score to something like a hash of the card number and in today's date. And what that means is that for any given card, either all of the charges will not get reversed and there's no possibility of the person continuing to try the same card over and over again, or that they do get reversed and you get to observe the outcome. So the idea here is that you want to group these events into, let's say, attempts by card and not just be totally independent from try to try. And last little sort of puzzle is, let's say we compute precision or recall using these estimators over rolling windows. So I'm going to estimate the precision or recall of my model over the past 2 months every day. What we observed initially is something like this, where there are dramatic swings in the values of the precision of the recall as estimated by the system. So any ideas why we might observe this behavior? Yeah, back there. We're not. So all we have is like fixed policy, block if the score is above 50. We evaluate the precision or recall as described above, and they tend to be constant for a while, and then they swing wildly after every now and then. So these like dramatic phase transitions. Yeah, back there.
You let something through with a very large weight and get it wrong.
That's exactly right. So what happens here is that if your weighting is such that there are events with incredibly high weights, let's say you have a propensity score of 0.00001, and that results in a charge of weight, let's say 10,000. Then one charge of very high weight getting through, if you classify it correctly, will result in a huge improvement to your model. Or if you classify it incorrectly, it will result in a huge hit to the model metrics. So what you want to make sure that you do in this case is that you never have weights that are too low, right? Because single high weight events can have a dramatic impact on your estimators. And that's it.
Excuse me, can I ask one question?
Sure.
If you go back, isn't that also related to the volume of transaction? Just like you're going to have around Christmas, which is shown there, which is not really your regular world.
That's probably true, but this behavior is observed sort of not just seasonally. You know, like this particular like very erratic behavior is not a result of Christmas. It's a result of these high weight charges.
Can you explain one more time? Sorry.
Right. So if you have a single charge that has, let's go back to this. Let's say charge 6 here had a weight of like 100,000. Right, then that charge would dominate the precision on the recall calculation. So if we got charge 6 correct, i.e. it was fraudulent, then our precision on our recall would be very, very high just based on this one charge. But if we got charge 6 incorrect, if it had a weight of say 10,000, then our precision on recall would be really low. Right, so if you have any charges that have a high weight, like what's happening here is we have a rolling window and we roll onto a period that has a charge of high weight, and we obviously misclassified it. Metrics went way down and everything looked really bad. And then after a couple of days, there was another high weight event. We classified it correctly, and then the metrics all went back up again. So you have to correct for sort of high weight instances, or you have to make sure that your sigma really is smooth and that this doesn't happen.
That weight is the probability of all of 1 over.
Yes, exactly.
Can you just rule it out by having the function go back down to 0, say, if you love 75?
Well, if it goes back down to 0, then you actually will have a.
You can cut off those high-weighted events.
Right. You want it to go back down to something that's banded away from 0, like say like 0.02. That way the max weight is 50.
Right.
Yeah. That's right. I'm out of time now. So just in conclusion, you can A/B test models. In reality here, by doing this methodology, you can evaluate infinitely many model variants offline just by sort of having these log lines and doing the weighting. And you sort of have more flexibility there for model evaluation and model training offline. And this is work done by 3 of my colleagues, Ryan Wang, Robin Kramer, and Lis Frezzi. And for shameless plug here, we are very aggressively hiring data scientists and engineers for ML. So if you know anyone, please refer them. And that's it. Thank you.